Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, now we continue this frame analysis using moment distribution method. Now is under step 2A. We will calculate fixed end moment, fixed end moment due to external loading. External loading. Okay, so fixed end moment due to external loading. So fixed end moment, we have to understand what is fixed end moment. So fixed end moment, basically whenever the element, the member is subjected to loading. The member is subjected to loading. Loading that is subjected on the member, and we need to distribute it to the nodes. We have to distribute it to join. We have to distribute it to nodes. So that is fixed end moment. So fixed end moment, actually the moment is actually the behavior. The fixed end moment is actually the behavior. So the sign convention that we use in the fixed end moment basically is based on the behavior. The moment will push back the beam to its original position, because due to loading the beam will deflect. Due to loading the beam will deflect. And what happened after that, we the fixed end moment, when the beam is subjected to loading, uh, and we have to assume that both end are fixed, and then there will be a moment at each end, and the moment will push the beam. Actually, the moment will push the beam to its original position. Okay, that is fixed end moment. And basically there are two types of fixed end moment, and under step 2A we will only consider the fixed end moment due to external loading only. Due to external loading only. So in moment distribution method, before we move further, in moment distribution method, I have summarized into four main steps. The previous step number one, we calculate K, stiffness and distribution factor. So this distribution factor will be used in the frame analysis. There are two types of frame analysis. There are no side sway frame and side sway frame. So under 2A, step 2, actually under step 2, we will analyze. We will analyze no side sway frame. So in analyzing no side sway frame, what happened to the original frame? So we have to remove delta from original frame. Original frame uh, is like this in the diagram. But whenever we move to step number 2, we have to calculate FEM due to external loading only. Means that we have to make the frame, change the condition of the frame to properly restrain frame. So how to do that? We will put an imaginary support at C, since the frame is moving towards right direction. The frame is moving towards the right direction, so we have to put an artificial support, a pin support at C, and due to that there will be the restraining force. So R is exists due to the pin support. So step number 2 is actually for table number 1. Table number 1. Step number 2 is actually for table number 1. Table number 1. In table number 1, we analyze no side sway frame. No side sway frame. Why we have to change the from original condition. Original means there are external loading and delta. Original. And for no side sway frame, we actually remove the delta by putting an imaginary support at C, so that the frame will not side sway. And because of that, we can calculate FEM due to external loading only. Don't forget, we have to put the support at C, so that we change the frame is changed to properly restrained frame. This is step number 2. Step number 2 is no side sway frame. This is for table number 1. So if for no side sway frame, for table number 1, we calculate fixed end moment due to external loading only, because this frame is now properly restrained frame. So remember the definition of no side sway frame. There are two. Number 1 is symmetry due to loading and geometry, and number 2 is properly restrained. Now we have changed this unsymmetrical frame to properly restrained frame. Okay. Okay. Under step number 2, there are three sub step. I summarize into three. 2A is to calculate fixed end moment due to external loading. 2B, we will build a table, and we will calculate end moment in the table using moment distribution. And after that, we have to calculate the R value. So this R value will be determined under step 2C. Okay, in this video, I would like to focus on step 2A only. Fixed end moment due to external loading. Okay, so by looking at the diagram, we have AB, member AB, member BC, and member CD. And member AB has no member load. There is no point load. There is no UDL. There is no triangular load that is subjected on the member. Remember, we only calculate fixed end moment whenever the member is subjected by the loading on the member or along the member. Okay, member BC has UDL along the member. Member CD has no load. So we will get fixed end moment from member BC only. And always remember, whenever we want to calculate fixed end moment, we will assume all as a fixed end. Fixed end. So we take up member BC. We take up member BC like this. Take up member BC like this. So this is actually the formula given in the textbook. So we have one beam with both end are fixed, A and B, but due to this, the fixed ended are B and C. So this is B and C. B and C. The W is 5 kilonewton per meter. The length is 6 meter. Length is 6 meter. The length is 6 meter. Okay, look at the beam. The beam. Okay, due to loading, the beam will bend. Due to loading, the beam will bend. So fixed end moment act at the fixed end B and C to push back the beam to straight position. So the fixed end moment is applied in this direction, so that when we apply fixed end moment in those direction at B and at C, the bend beam will go back to straight position. So this will bring us the sign of fixed end moment. So fixed end moment, please remember, due to external loading, so we will get the value one negative, one positive, because we have to compare with sign convention for moment distribution method. So this is actually FEM for B, C, and this is FEM for CB, and it is counterclockwise for FEMBC and clockwise for FEMCB. Okay, the due to behavior, it is one negative, one positive. One negative, one positive. Why we get one? First one is negative because of the sign convention that we use in moment distribution method. We the sign convention for moment distribution method is clockwise, clockwise positive. So FEMBC, since the direction is counterclockwise, it is negative. FEMCB, it is clockwise, same direction, it is positive. The formula is WL square over 12. Okay, so this is the fixed end moment. Fixed end moment due to external loading. Due to external loading. Okay, always remember that the fixed end moment is actually behavior, and we will always get, due to loading, we will always get the FEM sign, which is opposite, one negative, one positive, one negative, one positive. So from this we get WL square over 12 at position B is W is 5, WL 6, WL squared over 12, we get 15. We get 15, we get 15. So what is the value? So FEM for BC is equal to negative 15 kilonewton meter, and FEM for member CB is positive 15 kilonewton meter. Okay, it is 5 and 6. 5x square divided by 5 times 6 square divided by 12. It is 15. 15. So this 15 is the fixed end moment at position BC and position CB. In the table, this is the first member and moment in the table. The first member and moment in the table. So in the next video, we will look at how we distribute moment, and always remember that the the moment in the table that we distribute is joint moment. We do not distribute the fixed end moment directly, because fixed end moment is member and moment. Fixed end moment is member and moment, and we distribute joint moment, not member and moment. Okay, so due to that, we will continue uh, under step 2B to calculate end moment, for no such wave frame in the next video. Thank you.